fact, you should go from minus infinity to infinity for a general random variable. What goes under the integral sign? What's the expectation of the nth power? Well, remember what we have here. It's very simple. It's just the thing you're trying to find, namely x to the n times f sub x of x dx. There's an nth central moment. And again, any of you have been exposed to, and you should have been exposed to probability theory, this should be old hat to you. The nth central moment is the random variable x minus its mean, that thing to the nth power, expectation thereof. And that's simply, just like before, the integral of all possible values of what? X minus this constant x bar, all of that to the nth power times f sub x of x dx. So let's do a couple of things. Let's look at the 0th moment of x. That's basically the expectation of x to the 0. And what is that? What is x to the 0? Right, it's 1. So the expectation is simply 1. That's easy. The 0th central moment is defined as expectation of x minus x bar to the 0th power, which of course is x bar minus x bar, which is 0. I'm sorry, which is 1. It's not this. This is just 1. The whole thing is 1. But the first central moment is equal to the expected, as I said, the expected value of x minus x bar to the 1. And what's that equal to? What is this? Expected value of x is x bar minus x bar, 0. First central moment is 0. That's why it's called a central moment. The second central moment is defined as the variance. It's got a name. And let's see what that is. That's the expected value of x minus x bar quantity squared and let's write out what that is. If I square the thing inside, I'll get an x squared minus x bar minus x bar quantity squared. Let's write that down. Then I'm going to take the expectation. So expectation of the square of x minus 2 times x bar times x bar plus x bar squared. So what is that equal to? That's equal to the second moment minus the first moment squared. Let me correct this, write it better. The square root of the variance is simply sigma sub x. And what do you call that thing? Anybody the name? I hear it. Standard deviation. And it's a measure of how spread the random variable is about its mean. There's something else you probably have never heard of. It's the ratio of the standard deviation divided by the mean. And that has a symbol, capital C sub x, and it's called the coefficient of variation. And it's going to appear in our work. So it's just the standard deviation normalized by the mean. Okay, so these are just things you should be familiar with, except maybe coefficient of variation is new. Now I want to talk about some particular versions of this. I want to talk about something called the characteristic function. And its symbol is phi sub x of some variable, I'll call it u. And its definition is it's simply the expectation of a function of x, namely e to the j ux, where j is the square root of minus 1. We don't use I, we use j for the square root of minus 1 in engineering. Anybody know why? Yes. I is for current. So ohm shows that first. So we use j. And u, basically, is a real quantity. Okay. Now, by the way, just for note, if the exponents in that expression were negative, then you got the Fourier transform, something you've probably seen before. If not, just a comment here. And it has properties very much like other transforms, very much like the Laplace transform, for example. Now, if I do a Maclaurin expansion of this exponential, I'm going to get the following. By the way, when I write down phi sub x of u as an integral, what is it? It's the integral e to the jux times f sub x of x dx. That's what this expectation here means. That's when I say expectation of what? Of this function of x. How do you do it? You write it out, multiply by the density, and integrate. So this expression I just wrote down follows naturally from this definition. There's nothing strange about it. Expectation of a function of a random variable is that function times the density of the underlying random variable. Okay. Now I do a if I take e to the ju x and I write a Maclaurin expansion, okay, I'm going to get the following. I'm going to get e to the jux at x equals 0. And then the next term I'm going to get is a ju, because I'm going to differentiate basically, e to the jux times x minus 0, that's the Maclaurin right there, at x equals 0. Plus more terms, I'm going to get ju quantity squared times e to the jux times x minus 0 squared, just showing you what the Taylor series looked like, but Taylor series puts that quantity a equal to 0. And then again at x equals 0. plus dot, dot, dot. Now, what does that give me? That function will be e, what is this first function here? What's our first term? How much? 1, correct. So that's 1. What is this noise here? Plus, I'm going to get it. This next term here is going to give me what? I'm going to get a ju when x goes to 0. This is the capital X, I'm sorry, up here. When x goes to 0, this term goes to 1, but I pull the x out of here. So I'm going to get a jux over 1 factorial, just to give you the form. Next term is going to be a jux squared over the next factorial, which is 2 factorial, etc. So what this gives me, I'm going to put this now into the equation, this integral equation up here, and I'm going to get that phi sub x of u is equal to the integral of the density f sub x of x times what I just wrote down, 1 plus jux plus jux squared over 2 factorial, etc., dx. And that turns out, when I start doing the integration, 1 times f of x integrated is 1. The integral of f of x is 1. Plus ju x bar, I got x f of x, plus ju quantity squared, second moment over 2, plus dot, dot, dot. That means that when I said u equal to 0 now, derivative n times at 0, I'm simply going to get j to the n, nth moment of x. And of course, j squared is minus 1, etc. So what I'm showing you here is that this characteristic function we just defined, its derivatives, the nth derivative at u equals 0 gives you the nth moment. And I want to write that down as something worthwhile. So let's record this as an interesting result. I'll suddenly be able to generate the moments of the underlying random variable simply by differentiating n times. Now, I didn't have to put, should be reasonably well known. My proof was a little bit sloppy. I went through it quickly because I really shouldn't have to prove it for you. But I want to define a second thing now. I want to define something called the moment generating function, which is similar to what we have here. And it's this quantity m sub x of v, say, which is defined as the expected value of e to the vx. That's a definition. And of course, that's equal to, just for the reminding us, it's the integral of e to the vx f of x dx dx. And if you do the similar thing, you can see if you start differentiating and set v equal to 0, you're going to find, just like above, that the nth derivative of this moment generating function when u goes to 0 is equal to just the nth moment. That's why it's called the moment generating function. Not unlike the characteristic function, but without the ju squared. And let's go one more, because I'm getting a family going here now. Let's do something we've seen before. We saw the Laplace transform of the PDF of x. I'm going to write that down. The little density, PDF density of a random variable x. And because we're going to be using this in queuing theory, we're going to take an example, the random variable x as, say, the inter-arrival time or the service time. So I'm going to use as an example the PDF distribution function we're going to call capital A of x, which we know is the probability that x less than or equal to x. I'm using this as an example of the random variable I'm after, anticipating it's going to be useful to me where capital A turns out by the inter-arrival time density, which we'll talk about a little more later. Of course, it's PDF, the density, little PDF, is the derivative of A of x dx. And therefore, it's the derivative of this probability I wrote down. Now, the Laplace transform we can write down. Laplace transform of x, the random variable, we call A star of s. The capital A reminded us it came from the density based on the inter-arrival time A. And what is A star of s by definition again? It's simply the expectation. Remember, it's a Laplace transform, e to the minus sx, expectation thereof. Which, if you want the definition again by an integral from minus infinity to infinity of e to the minus st, I'll use x, I'm sorry. Let's use x. E to the minus sx f a of x, little a of x, the density. And s, of course, is the complex variable. We saw this earlier in our definition of a Laplace transform. But, of course, the inter-arrival time in the application is a non-negative random variable, so this minus infinity can go to 0 minus. I'm using 0 minus to include any possible impulse for a of t at the origin, which it will occasionally be. So just like before, if you start differentiating this baby and setting s equal to 0, what are you going to get? A star nth derivative at s equals 0 is equal to minus 1 to the n times the nth moment. So we've seen this thing over and over again with a different coefficient. Now it's clear that these three things I've circled, all relating to the nth moment, have the following relationship, which is easy to write out, and I'll do it for you. It says that the characteristic function phi sub x of a variable sj, I'm putting it in terms of s now, I'm letting v be sj, is equal to the moment generating function with respect to x of minus s, which is equal to the Laplace transform A star of s. And to remind you, the nth moment of x can be written in terms of each of these. It's j to the minus n times the nth moment of the generating function, characteristic function, phi sub x, nth derivative at 0, which is equal to the nth derivative of the moment generating function of x at the argument 0 is equal to minus 1 to the n of A star derivative at s equals 0. Okay, that's a relationship among these three, and that's worthwhile circling as well. Both of these are useful. You'll be meeting them again and again in our studies. So there's three ways to get the moments, all based on similar functions: characteristic function, moment generating function, Laplace transform. Now, all of that was for a continuous random variable. So I'm going to add in a discrete random variable while we're at it. Let's consider a discrete random variable. And it'll be a set of probabilities for that random variable. G sub k will be the probability that x equals k, has discrete values. So that x is discrete. Its probability distribution is G sub k instead of the density we wrote with little f sub x. And we're going to find that G at 1, okay, what is, I'm sorry, G is the Z transform. I better write that down for you. Let's define G of Z, as always, as summation G sub k, Z to the k. And we'll go over all possible values of k. And so I ask you now, what is G of 1? Excuse me. It's her job to turn off the phone, so blame her. You can't reach it. Okay. What is G of 1? Look at this expression up here. This one, when Z is 1, what do you get? Summation GK. What is GK? It's a set of probabilities. What's the sum of the probabilities? 1. What is G prime of 1? Differentiate this with respect to Z. You get k, gk z to the k minus 1. Set Z equal to 1. Get summation of k, gk. What is that? I guess I'm confusing you. What is summation k g sub k? That's what I'm asking. What is that called? Expected value. It's the mean of this random variable x, okay? So it's x bar. And while I'm at it, what's the second derivative at 1? Well, it's going to be k times k minus 1, gk summed, which would be second moment minus the first moment. You should have been suffering with some of this in the homework. I know we didn't have expectation in this homework round, but you saw it in my last lecture. Okay. You will certainly be looking at this in your next homework. Okay. So having done that, I want to move on to a slightly different topic now. I'm just talking about characteristic functions, etc., that give you the moments if you differentiate them. I want to now talk about sums of random variables. Now, you remember from convolution that if I add together two random variables, or two functions actually, let's take the convolution of two functions. They will happen to be PDFs. For f of t and g of t equal to 0 for t less than 0, they only exist on the positive half line, then we defined the convolution of f of t with the notation star with a circle around it, and g of t, and that was a particular integral, if you recall, from 0 to t of f of t minus x g of x dx. And if we take the Laplace transform of that, you would take the expression under the integral sign, multiply by e to the minus st, and integrate. What do you get? Anybody remember? If f of t has a Laplace transform f star of s, and g of t has the Laplace transform g star of s, what is the transform of the convolution of those two? The product. Does that sound familiar? We talked about that last time. So just multiply by this. Okay. So just warming you up to mixing some random variables. Now let's consider n random variables. This was for 2. And let's write it as following. Let's assume we have a random variable y, which is the sum of n x's. It's x1 plus x2 plus xn, capital N of them. And let's assume these are independent random variables. So I'm considering the sum. Well, what is the mean of y in terms of the moments of the x's? The mean of a sum is the sum of the means. So it's the mean of x1 plus the mean of x2 plus etc. Now I want to go further. For the moment I'm going to make n equal to 2. That means y bar is equal to x1 plus x2 bar. But now I want to get the second moment of this sum. Okay? So what is y second moment? It's equal to whatever this quantity is, it's x1 plus x2, that's y, squared, average. So let's work on that. When I square this quantity, I'm going to get x1 squared plus 2x1 x2 plus x2 squared. And I want the average of that. So I'm going to need x1 squared plus 2 x1 x2, but they're independent, so the average of the product is the product of the averages. plus x2 squared, average. Now it's also true that the average of y itself squared, well, I know what it is from this equation above. I know it right here. So square that thing, and what do I get? Let's write it out. I'm going to get the quantity x1 bar plus x2 bar squared, which is equal to x1 bar squared plus twice x1 bar, x2 bar, plus x2 bar squared. Those are all first moments. Now, finally, I want to get the variance of the sum, the variance of y. And what is that? That's the second moment of y minus the first moment squared. And let's write out from the things I just cooked up. Up above I have an x1 squared, x1 squared, second moment. So I just picked up, I'm going to circle in red these things that I pick up now. I just picked this up. Now I'm going to pick up this term next. Remember, I'm subtracting the second moment right there. So I'm going to have a minus x1 bar squared. Then I'm going to add in this x2, the second moment of x2, which I have, and subtract out its mean squared. And I'm left with all the rest of these two things. So I get 2 times the quantity x1, x2 bar bar, a common bar. Let's be careful of that common bar here. I'm sorry, this fellow up here should have been I haven't yet used the independence. Before I do, it's the average of the product. So I'm going to do x1, x2, and that's going to be a constant bar. Minus the individual moments, x1 times x2. Now, if they're independent, and I said they are, then I can break this. And this whole thing goes to 0. And so what am I left with then? I've got x2 squared, second moment, minus its first moment squared, and x1 second moment minus its first moment squared. So basically I got this variance of x1 squared plus, with variance, single squared, plus the variance of x2. Now, if they're not independent, and it's a homework problem you're going to get with that, you can't do this red thing. You'll have to account for what that is. It'll force you to remember that if things are not independent, you don't get that simple result. Now, in general, though, here I see if y is the sum of two independent random variables, the variance of y is the sum of the variance of each. So for n, and I'm going to use the independence now, the variance of y will be the sum, variance of x1 plus the variance of x2 plus dot 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 plus the variance of xn. So that was pretty straightforward. Again, I'm going to remind you that y is the summation of I equals 1 to n of xi. That's what we defined it to be. But now I'm going to, and these are IIDs, identically distributed independent random variables, the x's, with a mean x bar and a variance sigma sub x squared. So each of them is identically distributed, independent. But I'm going to change something on you now. I'm going to point out that the number, is a random variable. You don't know how many you're adding together. Now what happens? Okay, a moment ago, we knew it was exactly n, and that was a constant. Now we're letting n be a random variable. So let's say that. N is a random variable with mean n bar and variance sigma squared sub n. Now it's going to get interesting. F sub y of y, the distribution function for this sum, is what's called a compound distribution. It's compound in the sense that the number of elements is a random variable. And this gets really interesting now. I want to find the Laplace transform of this variable y. And by definition, what is that? That's expected value of e to the minus sy, whose inverse transform is basically f sub y of y. So if I got y star of s, I'll get little f sub y, the density. Okay. So y star of s is equal to expectation of e to the minus sy. How the devil are we going to do this? Magic. We're going to use conditioning to make it easy. If I told you that the value of the random variable capital N was some number, then it gets easy. So let's do that. I'm going to sum over all possible values of that random variable n, say from 0 to infinity. This is the first time you've seen the use of conditional expectation to make things easy. That'll be the expectation of e to the minus sy, given that this random variable n is equal to some known number n, and to uncondition what they'll have to do now. If I could write that down, that expression is not complete yet. What else do I have to write down? Do I hear something? I hear mumbling. Okay. I got to multiply by the probability of that condition and sum of all possible conditions. So I got to multiply by the probability that n is equal to n. Now, if I tell you there are exactly little n added together, then I can write this expression rather easily. That's a summation of expectation of e to the minus s. Now, what is y? In this case, it's going to be x1 plus x2 plus out to x little n, a known number. That was given the probability of n. That times the probability that n did take on that value. So let's write this out. That exponent breaks into a factor of n of these, n is 0 to infinity, of the expectation of e to the sx1 times expectation of e to the sx2 with minus signs, dot, 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 expectation of e to the minus sxn. All of that times the probability n equals n. Now, what is each of these guys? Remember, each of the x's I've added together is a set of identically distributed independent random variables. Each of those has a transform. What would be the transform of x to the I? E to the minus sxi. Well, here it is, e to the minus sxi. So that, in fact, is x star of s. Easy. And I'm multiplying how many of those together in this summation? Exactly n of them. Okay? So this sum, summation from n equals 0 to infinity of x star of s, there's n of them. Yes? It's built in because I put it up in the exponent, a little n. Given the n, so it gave me this n up here. But it's a good question. The question was, do we not need the condition on n? And it's built into the exponent here. Okay, so I got that times the probability n equals n. So I was able to write this down by introducing this rather important condition. Once I know what this random variable is, it has a value n, I can write down to the bottom line here. Now, does anybody see what that darn thing is? What does that summation look like? Excuse me? Summation of ziggle to the n, probability n equals n. What if that ziggle was z? Suppose you replace x star of s by the quantity z. It's a z transform. Of what? Of the distribution regarded to n. So let's identify the z transform for n now. Let's assume that, whoops, let me back that, black. Let's say that n of z is the z transform for g sub n. We said it's got a distribution. Here is its z transform, n of z. That means from the equation above that y star of s is equal to the z transform for n, namely n itself, at what value of z? X star of s. So I was able to write it down by being clever as to what condition I wanted to include. Now, I took you through this example to show you the power of conditioning. I didn't know how to write down y star of s up here. I didn't know how to write that down. I didn't know what to do with this. But once I condition it on this, I can write this thing down very easily, bang, 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 and get to that result. We're going to use that over and over again. Question?
Is multiplying the expectation condition with the probability of the condition like more advanced way to use Bayes theorem?
No, we didn't use Bayes theorem. We didn't turn things around. We conditioned on n and used that throughout. We didn't say n given y, which would have been Bayes theorem. Say that again, I'm sorry.
Why is it that you multiply the expectation with the probability instead of multiplying the expectation with the expectation?
Oh, how do you condition? The question is, why are we multiplying by this? And the answer is, think of what conditional probability is. Okay? failing again? What's the probability of A given B times the probability of B? That's probably A and B. If I sum over all possible B's, which I'm doing with this n here, I'm ending up probability of A, which is what I'm trying to find here. It's basically based on the definition of conditional probability. That's all it is. Okay, it's time to take the break, but I want you to review what I just did when you get a chance, because that process is going to be used over and over again. We're going to have complicated probabilities. So how the heck do we find its density or its transform? Condition it on something to make the answer easy. And as I say, to write this down is hard, but to write that down, knowing how many there are, was easy. There it is, and we know everything about the x's. So bang, we came out. And this was another interesting step. The first step was the condition to get this simple expression, and then to recognize that this expression happens to be a z transform. That's another kind of revelation. And we'll be doing this over and over again. We're trying to make the computation simple. Okay, let's take a break. Yes.
Did you decide when the midterm's going to be?
Yes, you weren't here at the beginning of the class, were you?
Yeah, that's probably why. I
Uh-huh.
have a class right before this on the other side of campus.
Okay.
So I have
Okay.
to like walk over.
Okay, I'll be putting this up on the website, by the way. But here it is. It's going to be the 12th of February.
12th? Oh man.
Yes.
That's the same day as my other midterm.
Well, I tried to satisfy in general.
it-
People,
did-
people, people complaining that this was a bad week for them. We could have made it on the 7th.
Yeah, I was fine with the 7th, but people are not fine.
That's right. There was. I think this is midterm week as well. I mean, we can move it back if the group. We can raise that issue again. But look, you're used to taking courses with midterm week, right?
I know, it's annoying to have it like back to back. I have like 12 to 2 and 2 to 4.
Understand.
It's fine.
You have the whole weekend to give it. If you want, I'll check. I mean, we can make it the 7th.
I'm fine with the 7th, the 9th, the 5th, anything.
Well, the 9th we can't do because some
Or
people.
on a Friday. Yeah, I'm
Right.
fine. Like anything like week 5 is perfectly fine with me.
I'll ask.
Okay, perfect. I
Okay,
appreciate
sure.
that. Thank you.
Okay. Yes.
Hey, I just had another question about
Sure.
number 3 on the homework. I
Okay.
was a little confused on how to do part B. So I don't have it up with me right now,
Yeah,
but
you
I
want
have
it-
my solution to part A.
What was the? I
This
want to
was the
remember.
question. I think it said that for n less than 0, f of n is 0.
Yes.
For n equals 0, it's f 0.
Right.
And then for n equal to 1, it's
You got this.
f-
Right. This condition.
And
Right.
then for n
And from 2 on.
from 2 on, it's
Right.
f,
And right. It's this. Right.
f of n equals f of n minus 1. So from that, this is what I
Let me find the exact problem here. I'll disconnect it from here. Okay, so for 3, oh no, that's a different one. That's the next homework set. So set 2. Okay,
It's this one right here.
right.
Yeah.
Oh, I didn't see you wrote that down. Was that there too?
That I just can't. I mean, it basically just cancels out the a plus b, right?
Say that again?
You can factor out a f of n minus 1. Oh, is that n plus
that-
1?
That's n minus 1, n plus 1. Yeah.
Oh, I've just misread. That's why.
I wrote it very clearly.
Yeah, you did.
Yeah.
Okay, so
Sure.
that would change my answer to part A. And then my answer to part B would make more sense.
You can hand it in, only making sure that you made an attempt. We're not grading the quality of the answer.
Oh,
you know.
okay, okay.
So don't worry about handing it in today.
Uh-huh.
But you can correct it for yourself, and I'll hand out the solutions on Friday.
Oh, okay, so like, how do you grade? Because there's no TA for the class, so do you grade the homeworks and the tests yourself?
I'm having somebody make sure that they were handed in. And it's not Shakespeare. It's
Oh, okay.
If
So
you
like,
hand it in, you get the points.
okay, so it's like basically completion, not
That's right.
completion and effort.
Well, think of effort, participation, really.
Okay, it's only 5% of the class.
It's only 5% of the class.
And the rest of it is just the test.
That's right.
And the test you grade it yourself.
That's right.
Okay.
For sure. No worry. Yeah. Yeah.
Okay, all right. I'll take a look at this and yeah, I just
Okay.
missed. I
Sure,
I,
sure.
I
That's what
read
I
that
thought.
as f of n minus 1, so I just factored
Oh.
it out. So I was like,
Oh.
okay, this is equal to a plus
Oh,
b
the
times
Fn
minus
equal to
1.
Fn minus 1,
Yeah,
right.
I'm like, yeah,
So it's
okay.
constant then, right?
Yeah, it's just constant.
Right,
That's what I
right.
got. I'm like, and then
No,
this made sense, but then when you try to plug that into part B, the answers all just not make sense.
Right, right,
So
exactly.
that's why I messed up. Okay.
Good,
All
okay,
right, now I
good.
know. Cool. Thank you.
Sure. Yes.
I have a question about the lecture here.
Yes.
So I've been going through this, and then
Mhm.
I don't quite understand here. Is this n still the random variable here, or is it a function?
It's the name of the Z transform for the probability distribution. Gn is a probability, right? I said that somewhere, I think.
So g is here. Is it this thing?
Yeah. Gk is a probability.
Uh-huh.
X equals B. That's K. That should be K.
Yeah, that should be k. Sorry.
Right. Okay. So there's a discrete distribution here.
Yes.
It has a Z transform. I'm calling that N of Z. So summation of GK, no, for N, GK has a Z transform, G of Z. And
Right there, right.
right, where's the N now?
And it's the final result is
Yeah, we don't,
on the next page.
right. And N of Z is its Z transform. Did I duplicate that? Actually, let me think. Just a moment. You maybe have a point here. Let's see. Sorry. And it was, just a second. Did I give G of Z? Did I write down G of Z?
You did.
Then I meant to write N of Z. I'm sorry, but let me check my own notes here.
So should I replace this n
Oh,
here
just
with g?
just one second. Did I say that actually? You're right. Oh. This was a general case
Yes.
talking about, but I didn't mean this to be the same. You're right. In place of G, I used N here. This was a general case for an arbitrary system. This was a specific case we're talking about. So you're right. It's confusing, and I'll mention that to the class.
Okay.
Because right here I said, you're right. You're quite right. I'll point out, and I'm using N in this example
Okay.
as opposed to the. But so
But-
what? So what's the problem then?
So
That could be a G as well, right?
this
right.
would be
Right.
that.
Same thing. Exactly.
I see.
Right.
I see. So I will just plug it back
Right.
in here, and then it's all out. Oh yeah, of course it works.
Yeah, I used two notations for the same
I
thing.
see,
That was
I
the
see,
problem.
I see.
Good. Good point.
Thank you.
Sure. Okay, let's get started again. One of your fellow classmates pointed out there's a little inconsistency in some of my notation. So let me get that up again. Where am I? So he points out that I defined, and good comment. I defined n of z to be the z transform of g sub n, but earlier in the more general case, I defined g of z to be the z transform. Same thing, I just used different notation. This was a more general case. Below here was a specific sum case. But if you want, if you're more comfortable, you can write g of z here as well. Just a notational issue. Okay. Now what I want to do now is give you some inequalities. Again, this is still regarding probability theory. And limit theorems. And what I'm going to do is give this to you without proof. But I just want you to be aware these inequalities exist. So the first thing I want to do is talk about something called the Markov inequality. And what I'm trying to do with these inequalities is to bound the tail of a density function. What's the probability that beyond a certain point, the probability is no more than so much? And now for a non-negative random variable, I'll give you the expression for the Markov inequality of that question. Non-negative random variable, let's call it x. The probability that x itself is greater than or equal to some number a is less than the mean of that random variable over a. Wow. Just knowing the mean, you could put a bound on the tail. It's not a great tail, but it's a tail. It's a bound. That's sort of, and it's a very simple, easy thing to prove, by the way. In fact, you might want to try it yourself. It's easy. Now, there's a slightly better inequality for the tail, and it's called the Chebyshev inequality. And you might wonder how to spell the name Chebyshev. And the answer is any way you like. Okay? It's a transliteration from Russian. And at some point, if we have time of the course, I'm going to present you with pictures of all these names of people I presented you, because they existed. You should see what they look like. Just get a little familiar. Oh, yes, I recognize. That's Laplace. Okay? Or Chebyshev, or Markov. I mean, these were real people. It's not arbitrary names. So we'll do that later when we get some time. Okay. So we're going to talk about variable x with a finite non-zero variance. And with a mean that's also finite. And the bound is the following. The probability that the absolute value of the random variable x minus its mean is greater than or equal to a. In other words, can it differ by its mean by very much? That's the question. And I'm going to say that probability has to be less than or equal to the variance of x over a squared. Again, wow. Just knowing the first two moments, you can say something pretty powerful. Now, another way to say that is the probability of this absolute value of x minus x bar being greater than or equal to a quantity called k sigma, k times the variance, the standard deviation, that is less than or equal to 1 over k squared. That's equivalent to the other. But it's very nice that knowing just the mean for the case of Markov, the mean and variance for the case of Chebyshev, gives you a bound. They're okay bounds. They're not great bounds. They're okay bounds. Okay. Now, getting away from inequalities for the moment, the third thing I want to mention, or just quote, is essentially something related to the law of large numbers. Can anybody tell me anything they know about this thing called the law of large numbers? Have you heard of it before? And if so, what's the essence of it? Has anybody heard of it before? One person and two people scratching their head. Okay. 3, 4. Okay. Okay. So let's discuss it. Let's have x1, x2, a whole sequence, be a sequence of IID random variables. It's an infinite sequence, in fact. Let's say that for sure. Of IID random variables. And each with an expected value for each one is equal to, I'm going to use the symbol mu. And I want to consider a particular function of those sums. I want to consider something that we call the sample mean. It's written as x sub n with a tilde above it, just to give it a different symbol, which is 1 over n times the sum of the first little n of them. It's called a sample mean. Now, the weak law of large numbers basically says the following, that this sample mean xn tilde goes to the value of the mean as n goes to infinity. That's really interesting. So let's take an arbitrary random variable with these conditions on the variance and the mean. Add a whole bunch of them together, divide how many you add it up, and you know the answer. That ratio is going to be the mean itself, no matter what that distribution is. For example, if I had a fair coin and I tossed it 3 times, comes up either heads or tails. Almost anything can happen. 3 heads, 3 tails, 2 heads and 1 tail. But if I tossed it 1,000,000 times, what can you say about the number of heads that are going to come? It's a fair coin. About the number of heads that are going to come up. Close to 500,000. I read your lips. Close to 500,000. Plus or minus a very small percentage. You know the answer ahead of time. By the way, that observation has been used exquisitely in many fields of science. For example, in information theory, that's what makes the second law of information theory, Shannon's second theorem, work, for example. You know the answer ahead of time. There's no uncertainty about it. This is very powerful, okay? Now, the weak law says it converges in probability. The strong law says it converges almost surely. I don't want to go into that. The point is, you add together a large number of independent random variables, each with the same mean. They're going to end up to tell you what the answer is. So again, this is telling you something about what happens independent of the distribution itself. Now, the fourth thing related to that, you might expect I'm going to get to, is a central limit theorem. Can somebody tell me what the central limit theorem basically says? Not mathematically, but in words. Yes. Right. If you add together a large number of independent random variables, doesn't matter what that distribution is, the distribution of that sum will look like basically a Gaussian distribution, a normal distribution. So not only do we know what a large number is going to give in terms of its average, we know what the shape's going to be. It looks like this. Now, if you start adding together 100, 1,000, 10,000, it's going to very quickly look like a Gaussian. I'm going to write it down in a minute. But what else can you say? What about the width of that Gaussian as you add together many? And suppose you divide that thing by the number you've added together. What's going to happen to the width of that Gaussian? Look at the law of large numbers. It says for sure that sum divided by the number will be the mean mu. So the variation, even though it's a Gaussian, it'll shrink and shrink and shrink. And for sure it's going to be the mean. On the way there, it's a Gaussian. Gets narrower and narrower percentage-wise. So the central limit theorem, we'll write it down in a minute, says more than the law of large numbers. It tells you what the shape is on the way to going to that value. Okay, so let me write this thing down. Basically it says, let's take a sequence of random variables, x1 through xn. It's going to be, again, be a sequence of IID random variables with mean mu and variance sigma squared. Each of them behaves that way. And let's say their PDF, probability density function, is, say, little f of x. They're identically distributed, so they have the same f of x. Let's do the same thing we did before. Let's add them all together. Let y sub n be the sum of all of them. Sum from 1 to n of xi. And let a different random variable zn be that sum yn minus the mean of that sum. What's the mean of that sum? Each one has a mean mu. There's n of them, so factor of n mu. That's the mean of that sum. And divided by basically standard deviation, which is the sigma, standard deviation, times the square root of n. That normalizes it. And the central limit theorem talks about the distribution of the variable zn. And it says, the distribution of zn converges to a standardized normal distribution namely with basically zero mean and unit variance. It's called n of 0 and 1 because I subtracted off the mean, so it's going to the mean, so it's going to take that in, and the variance will go to 0. This is as n goes to infinity. And typically, you don't need more than on the order of 30 or so. N can be on the order of 30, and you're really there very quickly. You don't need 1,000. 2 is not enough. 30, a number like that usually does it. And this whole thing is independent of the density of each of the x's. i.e., the limit as n goes to infinity of the probability that Zn is less than or equal to z, some constant z, is equal to this symbol phi of z, that's not the old phi of z from before, which is defined to be 1 over from minus infinity to z of e to the minus x squared over 2. That's a normalized Gaussian dx. Okay. We could prove it if you want, but it takes too long. You can find it in any textbook. Realize that we know something about the limit of a large number of random variables. It's a very powerful theorem. Now, I'm going to introduce one more thing without proof again, which is some little extra tool you can have. You may find useful. It's useful in cryptography these days, for example. It's used in information theory all the time. We won't be using it, but I want to show it to you anyway, okay? It's called, what number is this, 4 now? Yeah, 5. It's called the Chernoff bound, after somebody named Hermann Chernoff. And it says, once again, consider a sum of random variables. Consider y equal to sum, say, of n xi's. And again, the xi are IIDs. And I want to define something for this. We've already talked about it for the moment generating function. I want to define moment generating function for x itself, which we know what that is again. I'll remind you. It's expectation of e to the vx. Now we're looking for a way to bound the tail, just like Markov and Chebyshev. We want the probability that y is greater than or equal to y, and I want to bound that amount. Now, the value of giving this to you is because I want you to understand a beautiful idea that's come up. So let me plot the density on y, whatever it might be. By the way, if n is big enough, what does y begin to look like? A normal. That's what the central limit theorem said. So I'm going to draw it looking like a normal, more or less. Let me do that here. Sort of a normal, okay? And suppose I'm asking for this quantity up here, which says, what's the probability that's bigger than y? So let's identify y on this axis. Suppose y is right there. Then I'm asking for how big is that area? That area is the probability that capital Y is greater than or equal to little y, right? That's what this expression up here is asking for. Which means I want to take this f sub y of y and multiply it by the following. Oops, let me make it red. What did I just draw as a name for that function, that red function? Come on, what is it called? Unit step shifted to y. Which says if I multiply red by black and integrate, I get the green hatched area, right? And that's what I'm trying to bound. It's complicated. But look at the magnificence of this now. Suppose I draw another function, and I'll try to draw it well. Maybe this will help me. Let me start again. And I'm going to tell you what that function is. It's e, it's an exponential, times v of w minus y, where w is this axis out here. And I should have called this a w also right here. Now, isn't it true that blue is bigger than red? I've designed it that way. So if I integrate blue times black and integrate, okay, what will I get? I'll get a bound on the green area. I will have overstated it, right? So whatever I get for that, if I do the blue, I'll get that the, just a moment, the integral, let me just say it in words, integral of blue times black is giving me too much, right? So that's basically overbound this tail. Now, I have a little freedom here that quantity v is a free variable. And if I choose it optimally, I'll get the best bound I can. And that's what Chernoff did. So let me define another quantity for you, and that'll give you the result. I'm going to define something called the semi-invariant generating function. And I'm going to use gamma for that. Let gamma of v be the logarithm of the moment generating function. And given that, with a little bit of calculation, and we can prove this if you like, the net result is that the thing you want to bound, the probability that y is greater than or equal to n times the differential of this gamma function at the argument v for this random variable x, that is less than or equal to e to the n times gamma sub x of v minus v times gamma prime of x. Now that looks a little, that's a v. I'm not telling you how to get that, but I'm telling you that is the Chernoff bound, and it tells you how big the tail can be. The probability of random variable is bigger than so much is less than a number you can write down. And it's a pretty good bound. It's better than Chebyshev, better than Markov. It's a lot better, in fact. Now, an even better way is to figure out what the Gaussian distribution is and integrate that tail. But that's very complicated. This expression happens to give you a very nice result. Okay. End of story. That's the end of the probability discussion. What I want to do now is to move on to queuing theory. So let me pull up the right notes here. Okay, now I've already given you a little bit of an introduction to queuing theory early on. But this is really where the class should have begun if you had your prerequisites. Okay? I'm not finished torturing you yet. There's some more material I'm going to bring in which you may or may not have seen before. But I want to introduce some notation and some a particular result. Remember what we're looking at? We're looking at unsteady flow, random flow, through a single channel, where the rate has to be less than capacity, whatever that means. So let's draw a picture again. It's a queuing system. And in our model, it consists of a queue. And we're going to start with a single server. And customers arrive from outside. They leave the queue, enter service, get served, and leave the system. So this is what we call the queue. This is the server. And the arrivals come in. Here they come. And here they go. They're leaving. So these are the arrivals. And these are the departures. That's called a queuing system. Let's talk about the arrivals. The arrivals each have an inter-arrival time, time between arrivals, and the PDF, the density function of that, little p, little d, little f, we call A of t. A standing for arrival. That's a probability density function. And the service basically has a service time. How long do you spend in service? It's random. PDF, which we're going to denote by B of x. Why B? Because it comes after A. Okay. Now, the arrivals come in. They need service times. That drives the system. So what do you want to solve for? I mentioned this earlier. We want to find the following. For example, the number in system. How large is the queue? How many people are in the system? Is your buffer big enough to hold them? Kind of question. Now this may be a function of time or maybe steady state behavior or whatever. Also you want to know how long do you spend in the queue? I mentioned this earlier. Waiting time in the queue. Also you may want to know the time in the queuing system. By that I mean queue plus service. And there are other things we could ask about. We're going to keep it relatively simple in terms of the structure. I mentioned there's a lot of weird things that can happen. For example, people can leave, they can enter and decide to leave before they get served. Or they can start arriving and say, I don't want to join. Or the server can say, I'm not going to serve anybody, he goes on vacation. Or there may be priority ordering. People who pay more get served first. There's all kinds of behavior you could assume. Maybe there's a charge. If the server goes on vacation, comes back, there's a cost and delay. We're going to ignore those in most of what we study. Many of those things have been studied, but I don't want to drive you crazy. But in terms of these A's and B's, we have notation for specific distributions, okay? Symbol M will mean it's an exponential distribution. Namely, in the case of the interarrival time, A of t will be lambda e to the minus lambda t. In case of service, B of x will be, say, mu e to the minus mu x. Or there's another kind of distribution we use. It's called E sub r. That E stands for the name Erlangian. It's called an R-stage Erlangian. Or it can be used as symbol H sub r, which will stand for an R-stage hyperexponential, which will show you what those distributions are later. These are all well-known distributions. Or the symbol D stands for deterministic. Namely, there's nothing random about it. Every 2 seconds, somebody comes in. Each person that comes in needs 1.5 seconds for service. Bang, 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 bang. Very simple, trivial system. Or we could use a symbol G to say it's general. I don't know which of these it is. You tell me what the distribution is. I got to give you a solution. Okay. Now, in order to use notation using these variables, there was a particular shorthand notation, and it's the following. You write down the symbol A to describe the interarrival time density. It'll be perhaps one of these I've just shown you here. Slash, for B, you describe the service time. So, for example, an exponential interarrival time and a deterministic service would be MD. Then the next symbol is a little m. That's the number of servers. The next symbol is capital K, which is basically the storage capacity. How many can you hold in the system? And the last symbol is another m, where m stands for the size of the population. So let me just write down some of that. M out here is the size of the population. Namely, it may be that you can only have 100 customers that are circulating around. You can't have 101. So this is the population size. This K is the storage capacity. Usually that includes the guy in service. So how many can there be in the entire queuing system? If you can only hold 5 people and the 6th person tries to arrive, they can't come in. And this is how many servers there are. Maybe there's more than one clerk in the store that's serving you. And we will usually, and most of what we're going to study here, we'll usually assume first come, first serve. First come, first serve. Also known as FIFO, first in, first out. Okay, so usually we only have the first 3 of these symbols right here. The other 2, if they're not there, K is assumed to be infinite and M is assumed to be infinite. So usually the default here is assume there's plenty of space and plenty of customers. But ABM is the place where we make some variations. Okay. Now I want to make a few definitions. I'm going to let the symbol C sub n basically denote the nth customer to come in. N is time. Denote the nth customer to arrive. So if you want to draw the queuing system again, out comes a couple of customers, say. This could be the 5th customer. Behind him or her would be the 6th customer, C6. And coming in, we got a bunch of customers. This could be, say, the 32nd customer come in. Behind him or her will be the 33rd customer. So it's all timed with numbers. Given this picture, how many are in the system? What is it? Yes? 26. 7, 8, 9, 10, etc., all the way up to 31. Okay. So it's a very simple picture. We don't try to confuse you yet. Okay? More definition. Let N of t be the number of customers in the system. Remember I said I want to find that. At time t, in the system, the whole box. So that's a time variable quantity. Similarly, I'm going to define something unusual now. I was going to call it U of t. U doesn't stand for the word unusual, by the way. It stands for something called the unfinished work. In the system at time t. And what is that? That's equal to the time required to empty the system of all customers present at time t. So you come in, there's a certain amount of work to be done. I'm asking how much is that work? That's what I call U of t. It's the unfinished work in the system at the moment. Some people call that basically the virtual waiting time. We'll explain why and why that's not an especially good name. Now, we can draw some conclusions now. If U of t is greater than 0, strictly greater, then the system is busy at time t. There's work to be done. On the other hand, if U of t is 0, then the system is idle at t. So I want to draw now a time axis, which we're going to use over and over again. It's a very convenient one. It's a double time axis. So let me draw it right here. This axis is telling me what's happening at the server. And there's another axis I'm going to draw. And that's what's happening in the queue. And both of these are time axes. So let's see some things happen. I'm going to start to draw this in red now. Let's assume that at this point in time, Cn arrives. So I'm going to say that. Cn comes in. And he joins the queue. Now I've given you some notation earlier, if you remember. Maybe I should repeat it here. Do you remember the notation for the time when this guy arrives? Way back a couple of sessions ago, we called that tau sub n. So let me write down what that means over here. Tau n is the arrival time of Cn. That's when he arrives. Now before him, somebody else came in. I'm going to call him, what's the name of the guy that came in just before him? Cn minus 1, right? Let's assume that happened here. And let's, for the heck of it, just say that Cn plus 1 leaves the queue and goes into service at this point. Notice he's leaving the queue axis, going to the server axis. So this is Cn minus 1. So when Cn comes in, what does that tell you? The guy before him is still in the queue, so Cn has to join the queue. System is not empty, so he can't. There's only one guy in the queue at a time. There's a single server. Okay. Now, I have notation for this quantity here. Oops. That's little t sub n, because you may or may not remember t sub n is the inter-arrival time between n minus 1 and n. Between Cn minus 1 and Cn. Okay, now at some point, Cn minus 1 will leave. Let's assume that happens over here. Now when Cn minus 1 leaves, what else happens? Cn goes into service. He's the next guy up. So let's mark that in red because he's the red customer. And that means I can do something else as well. I can label something here. Let me get a straight line here. That means that this interval that I'm drawing right here, what does that interval mean physically? He came in time tau n. He goes into service at this other time. How long is that? Where was this customer all this time? It was in the queue. So this is what I'm going to call W sub n. Let's write it down here. W sub n, oops, let's get the black again, is the waiting time in queue for Cn. And that's something I'd like to be able to calculate. Now, sometime later, our good friend Cn is going to leave. Let's assume that happens here. Now, what can I say about the interval I'm about to label? What is that arrow I just identified? Service time. Cn went into service here. He left here. That interval must be xn, which I call the service time. Now, did I define xn anywhere? No, I didn't, so let me do it right here. Xn equals the service time for Cn. And by the way, while I'm at it, I'm going to write this in blue. If Tn is the inter-arrival time between Cn minus 1 and Cn, how is it distributed? Density y is A of t, inter-arrival time density. And for service time, how is that interval distributed? B of x, service time density. And all of these things are independent of n, because it's basically, we assume the inter-arrival time between adjacent customers has the same distribution. Same for service time. Okay. Now, we can write here that the sequence T sub n, which is distributed like A of t, and the sequence x sub n, which is distributed like B of x, basically drive the queuing system. They're the inputs. To the queuing system. That's all we know. And given that, we have to calculate some things. That'll be our job for the rest of this quarter. Now, there's something else I can identify here, and I'm going to draw it in a red arrow. I can draw the arrow from here to here. What did I just draw? What is this thing, this large arrow I just drew? The time in system. I'm going to call that S sub n, and I'll denote it, identify it here. S sub n equals the time in system. For Cn. And by the way, Sn can be written in terms of some of the known variables. It's the time in queue, Wn, plus the time in service, Xn. So this is a very handy diagram to see what's going on in the queuing system. We're going to take advantage of it later as well. What I do now is remind you of some of the variables. So I'm going to draw a box here. With 5 columns. And I'm going to need 4 rows. So let's first of all talk about the inter-arrival time. Thank you. The inter-arrival time, what is the capital P, capital D, capital F, the probability distribution for that? What's the symbol for it? Or, to make it a little bit easier, what's the probability density function? We called that A of t, didn't we? And the distribution function is capital A of t. And the Laplace transform, LTF, is A star of S. If I do the same thing for the service time, I'll get capital B of x, little b of x, and B star of s. This is summarized notation. For the waiting time, the PDF is capital W of y. I'm defining that now. the density will be little w of y, and the transform will be w star of s. And the system time will be capital S of y. That's a distribution function. The density will be little s of y, and the transform will be capital S star. So that's just a way to remember what this notation means. Okay, next time we're going to pick up on this and establish one of these important and simple results for queuing systems. So your homework is due today. I'll post the solutions Friday. I'm going to hand out the next assignment on Friday. It'll be due the following Friday. We're slipping one because we skipped this last Monday. We're not skipping an assignment, we're skipping a day. I'll catch up later. Okay. We're done. Yes, Rohit? Oh, yes. We did decide on the midterm date. Is everybody comfortable with that besides this one young man? Midterm I've got for Feb 12. Anybody hate that? You don't like that? How about Feb 7th? Who doesn't like Feb 7? Are we agreed on Feb 7? It'll be less material, which is good or bad. That means the final is going to be a little heavier.
Is the final cumulative or not?
It will be, but I'm going to focus more on the last half. Yeah, the final will be covering everything, but we'll focus on the last half. 7th midterm? Everybody seems to like that. Good for you. Okay.